Okay, so in the next few videos, we are going to start looking at the transduction of different kinds of stimuli, different kinds of sensory information. But before we can do that, we first need to talk about waves, because visual and auditory stimuli both occur in the form of waves. So visual information comes in the form of light waves, and then auditory information is in the form of sound waves. So we need to look at the properties of waves because that then corresponds to various properties of sound and vision. So the first thing I want to talk about is the amplitude, and that is the height of the wave measured from the peak to the trough. Okay, so the height of the wave. And then the wavelength is measured from peak to peak. Now, the wavelength is important because that is then directly related to frequency. And so frequency is just referring to the number of waves that pass a given point in a given amount of time. So obviously, the shorter the wavelengths, that means those waves are closer together, and you're obviously going to have more waves in a given time period. So the frequency is higher. Okay, so shorter wavelength, higher frequency. When the wavelength is longer, so when these peaks are more spread out, obviously the frequency, the amount of waves in a given moment is much lower. So longer wavelength, lower frequency. Shorter wavelength, higher frequency. Now, if we move on to light waves specifically, when we're looking at something, we're not actually looking at the object itself. Instead, what is allowing us to see that object are the light waves that are bouncing off the object. Our sensory receptors in our eyes don't detect objects, they detect light. So when you're looking at an apple, it's not the actual apple itself necessarily that your sensory receptors in your eyes are picking up, but the light that is bouncing off of that apple is what the sensory receptors are responding to. Now, light is a form of electromagnetic energy, and as you can see here, there are various types of electromagnetic energy, all the way from gamma rays down here to radio waves at the end. And what distinguishes all of these is their wavelength. So that's what you can see here. Gamma rays have a much shorter wavelength. Radio waves have a much longer wavelength. Now, the part that humans can see, the visible light that we can see, falls in the middle. So that's what we have here, visible light. Obviously, there are other species that can see various wavelengths, and so maybe able to see some of these other forms of electromagnetic energy. But as humans, the only type of electromagnetic energy that we can actually see is this small amount here. And we're actually going to come back to this, but first of all, let me talk about how these correspond to color. So the question is, how do we actually see different colors? We're going to look in the next video at different theories for how our sensory receptors respond and allow us to see color. But we also need to talk about how the various aspects of waves correspond to color. So the wavelength, so remember that's the length that between one peak to the next peak of a wave, that determines the color we see. So when we're looking at something red, the light waves bouncing off of that have longer wavelengths, and that's what allows us to see red. Greens have an intermediate wavelength, and then anything that's kind of blue, violet has shorter wavelengths. So if I just go back to this, down this end is obviously the shorter wavelengths, and up here is the longer wavelengths. And if you look down here, it shows you the color spectrum that corresponds to. So with our shorter wavelengths, we have our blues, our purples. In the middle, we've got our greens and our yellows. And then with the longer, as the wavelengths become longer, that transitions into oranges and reds. So the wavelength is determining the color. The amplitude, so remember that's the height of the wave from the peak to the trough, that then determines how bright or how intense that color is. So the larger the amplitude, the brighter that color will look, or the more intense that color will look. And then similarly, just like with light waves, the properties of sound waves then correspond to different aspects of sound. So if we start with the amplitude of sound waves, that determines the loudness, okay? We measure this in decibels, we'll use this little dB to symbolize that. So the higher the amplitude of the sound wave, the louder the sound, and then the lower the amplitude, the quieter the sound. And so what you can see here is kind of the spectrum of loudness and what that corresponds to. So a regular conversation is around 60 decibels. If we go up here, we've got a concert here that is 120 decibels, and that is above kind of the threshold where we're at the risk of hearing loss. So that's why, you know, you might have noticed if you go to a really loud concert, when you leave, you can't hear very much after, or you have a ringing sound in your ear for a while, and that's because of how of the intensity, how loud the sounds that you were around were. The next component to discuss is then frequency. So again, we're talking about wavelength here, how close those waves are, how far apart they are. The frequency is measured in hertz, and this corresponds to the pitch of a sound. So the higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. Now for humans, the audible range is between 20 to 20,000 hertz. There are obviously species that can hear a wider range or a smaller range. So for example, dogs can hear beyond 20,000 hertz. They can hear pitches that we cannot physically hear. But even within humans, there is still a variation in what can be heard. And it really depends on age. So as we get older, the first thing that we lose, sorry about that. The first thing that we lose is our higher frequency sounds, at those higher pitches. And so you can actually test this. What we have here, the mosquito ringtone. This is a ringtone that had the 17.4 thousand hertz. Because of how high the pitch is, older people cannot hear this because they've already lost that part of hearing. And that's really just the result of noise pollution over time. We lose those higher pitches. And so if you want, you can pause and you can watch listen to this little clip, and it plays different pitches, and it will tell you, if you can hear this, you're probably under this age. And then the last one that it plays is the mosquito ringtone. What I will say is that I have tried this in class with students, and when the majority are under the age of 24, I can't hear it. I am over 24, I can't hear it. The majority of the class, when I play this, have said they also cannot hear it. Now, at first I thought, well, maybe it's because there's something wrong with the video, maybe there is actually no sound being played. But I then played it in the presence of my dogs, and both of my dogs reacted to it. So there is a sound, but I can't hear it. Some of you may be able to, you may not. My thought process with those of you that maybe cannot hear it, if you are under the age of 24, I think it's most likely due to the amount of noise pollution within our society. I have a feeling, it says that we should be able to hear that under the age of 24, but if we're around extremely loud noises, we go into concerts and kind of damaging that part of hearing, then that might explain why not everyone can hear it under the age of 24. But you can test that out and see if you can hear it.